In the previous lecture we were discussing about the Navier Stokes equation and its derivation. In this lecture we will try to identify some problems, physical problems, where the exact solution of Navier Stokes equation becomes possible. These problems are limited in number because most of the practical problems are essentially non-linear problems, but there are certain cases where the practical problem is also a linear problem. So, the first example that we will consider is a pressure driven internal flow. So, the physical situation is something like this. I will draw it here. There are two parallel plates. Just take this example. This is a simple but a very elegant assumption of an internal flow. An internal flow means what? That you have a confined passage within which the fluid is flowing, and maybe the fluid is driven by a pressure gradient. Now, the flow may be closed from all directions, like you have a rectangular or a circular duct, but if the width of a rectangular duct is much larger than the height, then that may be treated as two parallel plates because the end effects are neglected. That is called as a parallel plate channel. So, let us assume such a parallel plate channel. This is the center line of the channel, and fluid enters from far stream with a velocity u infinity. When the fluid encounters the solid boundary, what will happen? Let us consider one particular section. Because of viscous effect, the fluid will come to a standstill at this location. This is called as no slip boundary condition. Then the velocity somewhere above it will be greater than 0, but also not the maximum one. In this way, it will come to a state when the velocity will become its maximum, and then it will not further change. Okay. If the boundary condition everything is symmetric, here also no slip, the same thing will happen on the other side. You go to a section which is little bit advanced, you will find that because you have entered more into the channel, the wall effects are more penetrated. That means there will be a greater depth from the wall up to which the viscous effects are felt. So, this velocity gradient will be felt say up to here as an example. Finally, something interesting will happen. Before understanding that, if we now draw the locus of these points within which this wall effect creates a velocity gradient, will sorry. So, we will have something, this blue line, which is called as edge of the boundary layer. And why boundary layer? This is the layer close to the solid boundary where the viscous effects are felt, that gives rise to the velocity gradient. So, this is called as boundary layer region and this is called as a core region. When the boundary layers merge, not exactly from here, but somewhere nearer in the nearby location, if you draw the velocity profile, then the difference between that location and this location is that in the developing region, this so called region where the boundary layer is growing, the core fluid does not understand the effect of the solid boundary, but beyond this the entire fluid understands the effect of the solid boundary. So, we say that the flow has become fully developed. And then this velocity profile does not change anymore. Whatever it is appearing to change is because of my poor drawing, but in reality keep in mind these are same, they are not changing with time. So, this region is called as a developing region or entrance region. This region is called as fully developed region. Just for the sake of understanding better, so fully developed region is a region if this is the x axis, u is not a function of x anymore. Just for the sake of understanding, let us try to make some plots. Core velocity versus x, wall shear stress versus x, and pressure versus x. So, first of all, let us say we consider two sections 1 and 2. Can you tell that out of these sections 1 and 2 where the core velocity will be more? See what is constant between sections 1 and 2? The flow rates are constant, and let us say that rho, the density, is constant, that means the volume flow rate is also constant. How do you get the volume flow rate? It is integral of the velocity profile across the cross section. So, if you come from 1 to 2, what is happening? The boundary layer is thicker, that means there is a thicker region over which the fluid is decelerated. To have the same flow rate, the region in which it is accelerated, there the velocity should be more, because the integral of this is same as the integral of this. That means the core velocity at 2 is greater than the core velocity at 1, till it becomes fully developed and the core velocity does not change. So, wall shear stress. So, for wall shear stress, first we can consider the fully developed region. So, what is the shear stress? The deviatoric part of the Newton's law of viscosity, and we are in fact the deviatoric stress is what that dictates the Newton's law of viscosity, that is mu into del uy del xj plus del uj del xi. So, at the wall there is no V. We will see this later on, that why V is 0 at the wall. In fact, there is nothing that requires a proof of this. Why V is 0 at the wall? It is no penetration boundary condition. U is 0 at the wall because of no slip. V is 0 at the wall because of no penetration, because the fluid cannot penetrate through the wall. So, because this is 0, tau wall is mu into this one. Because the fully developed velocity does not change with x, the wall shear stress also does not change with x. So, the wall shear stress will be something like this. But the question is, what is the wall shear stress in the developing region? So, the wall shear stress, this is of the order of mu into UC by delta, where UC is the core velocity and delta is the boundary layer thickness. So, this is UC and this is delta. The interesting part of this is that as you move along the entrance region, UC increases, we have just seen that, and delta also increases. So, how do you know their ratio, whether it will increase or decrease? So, here we use a physical judgment. What is the judgment? When the fluid just enters the channel, delta is tending to 0, but UC is finite. So, tau wall will be very large. So, it can only come down asymptotically from such a large value and it cannot blow up. Therefore, this will be the shear stress. What about the pressure? To understand the pressure variation, let us take again let us consider a region in the fully developed, a fluid element in the fully developed region. Okay. So, there is a wall shear stress, here is a wall shear stress. Let us say this length is dx. So, the force is tau wall into dx into the width of the element, that is 1. If this is h by 2, and this is also h by 2, then you have a force due to pressure here, P into H into 1, and here you have P plus dP into H into 1. So, we are assuming that P is only a function of x and not a function of y. This assumption can be justified from the y momentum equation, where P variation of y is 0, because there is no y component of velocity. We will see that later on when we discuss the full Navier Stokes equation. So, this is P into H, this is P plus dP into H. For a fully developed flow, there is no acceleration, the velocity profile is not changing, that means all forces are balanced. So, P into H minus P plus dP into H minus 2 tau wall into dx is equal to 0. So, tau wall is h by 2 dP dx, right. So, if tau wall remains constant, dP dx also remains constant, that means P versus x will be linear. So, P versus x in the fully developed region will be linear, and in this region it will be non-linear. Okay. So, this kind of qualitative depiction without getting into much of a mathematics, but getting a physical picture of how the basic variables are varying is very important to develop in physics and engineering. Now, for the remaining 10 minutes or so, our focus will be this region, this fully developed region, where the velocity profile is qualitatively sketched like this. Our objective will be to derive this velocity profile. Fully developed flow between two parallel plates. This is called as this one, plane Poiseuille flow. So, let us assume 2-dimensional plus incompressible flow. So, you have, imagine two parallel plates, the center line is x axis and this is y axis. This is the incompressibility equation. So, for fully developed flow, u is not a function of x, which means that v is not a function of y because del v del y is 0. Now, at y equal to h by 2 or minus h by 2 both, V is 0 because of no penetration. So, V is equal to 0 at y is equal to plus minus h by 2. This has nothing to do with no slip, it is because of no penetration. So, this means that you have V is equal to 0 for all y. So, when V is equal to 0 for all y, we can write that in the Navier Stokes equation. So, let us write the x momentum. This is the just traditional way of writing. There is no body force, so I am not writing any body force here, and we will write the y momentum. These are essentially the Navier Stokes equation. So, all the assumptions of the Navier Stokes equation will be valid. We now assume the following, we assume it is a steady flow. So, this is steady flow. Then because it is a fully developed flow, this is 0, and the corollary of fully developed flow is V equal to 0 provided there are no holes at the wall. If there are holes at the wall, then that will not be the case even if the flow is fully developed, but here there are no holes at the wall. So, when there are no holes at the wall, you have V equal to 0, then u is not a function of x. So, for fully developed flow this is 0. In this equation all terms are basically V related terms, so that is 0. So, the y momentum equation finally gives us, that means P is not a function of y. Okay. So, because P is not a function of y, we can get back from here and write this as dp dx instead of del p del x. So, what we are left with is the simple x momentum equation, that 0 is equal to minus dp dx and u is also a function of y only. So, this will become so you will have d2u dy2 is equal to 1 by mu dp dx. So, physically what it means is that the pressure force due to pressure gradient is balanced exactly by force due to viscous effect, and that is how the fluid is not accelerating. So, if you integrate it, you have du dy and u is equal to now, because it is a symmetric problem, we can just have half of the domain and solve the problem very easily. So, at the center line at y equal to 0, at the center line you have du dy equal to 0, right, because it is symmetric, u is maximum at the center line and that means C1 is 0, and at y is equal to h by 2 u is 0, no slip. This means 0 is equal to 1 by mu dp dx h square by 2 plus C2, right. Therefore, C2 will become 1 minus 1 by 2 mu h square dp dx. So, u is equal to 1 by 2 mu dp dx sorry, this is h by 2, right. So, this will be h by 2 whole square, right. Right. So, clearly because see y is always less than h by 2, but dp dx is negative because fluid is being driven by a gradient of from higher pressure to lower pressure. So, this minus into minus will make it plus. Sometimes the pressure gradient is not measured, but the flow rate is measured. So, it is possible to express this in terms of the average velocity. Average velocity is defined as integral u dy from minus h by 2 to h by 2 divided by h. So, this is the average velocity conceptually is what? An equivalent velocity which could have prevailed had the velocity profile been uniform and the same flow rate would have been maintained. So, this is the flow rate and this is the area, because you know h into width, width is cancelled in both numerator and denominator. So, this is the average velocity. So, if you calculate this one and plug in here, you will get u by u average is 3 by 2 into 1 minus y square by h square, and this is a parabolic expression. So, this is the expression of the fully developed velocity profile through a parallel plate channel, which is the so called plane Poiseuille flow. So, we have today discussed about some exact solution of the Navier Stokes equation, and we will continue with that in the next lecture. Thank you.